Welcome back. This is our last lecture of the day and the second econ talk in a row. So it should be fun, and I think this is a topic that really brings in a lot of different issues that we've been talking about throughout the day and during the breaks. So I'll just hand off to Eddie for the last talk of the day. Thank you.
Okay, thank you very much. Can everyone hear? Is this okay? I kind of managed to bang this and it fell open, so hopefully it's still working. It's a real pleasure to be here. Thank you, Adam. We have the sort of brief today is that I should give a talk which could be of general interest to people with a mathematical background. So this has got much less. In fact, it's got almost nothing that is kind of very particularly electricity focused, but at the same time, I actually think it's really interesting and has a lot of applications in one part of the electricity market world. So what do we agree on when we disagree? And more precisely, this is about forward contracts with private forecasts. This is based on a paper with Andy Philpott, who's sitting over here. So any difficult questions I'll throw in his direction. And that paper appeared in the first issue this year of Operations Research. So what I'd like to do is talk a little bit about how this all works, give an introduction to the idea of contracts between players with different forecasts. I'm going to talk a little bit about the sort of setting in a wholesale electricity market context. I'm going to say something about a very simple model for risk-averse firms who have different forecasts for the spot price. And then we're going to get into a discussion of different ways that agreement can be reached. So I'm going to compare what I'm calling direct negotiation with arrangements through a broker, and we'll see what that means in this context. And then we're going to get a little bit more complicated. I'm going to talk about equilibria and how supply functions can play into that. And then finally, right at the end, I'll make some remarks which I think are natural in this context of what sort of deductions we can make from the other firm's behavior. So that's how we go, and let's start off with this. I call this a betting game. I'm not sure that's the right terminology, but bear with me and we'll just go through this simple example. So player A and player B are seeing a succession, you can think about a historical sequence of events that are either red or green. So the red here is, I'm going to call it W plus 1, green W minus 1, and we can think about these in an electricity price context of high prices and low prices. I'm not going to be very specific, but we'll come to this later. Okay, so there are two possible outcomes only. Now the thing that we said right at the beginning is, how do we agree when we disagree? And the disagreement here that we're talking about relates to what the probability is of these high and low prices. And I've indicated there that we have player A who believes that the red dots are going to be 60% of the time out in the future, green dots 40% of the time, so they have a considerable range of disagreement here. And I'm going to use the letter rho with a subscript to mean those probabilities. So they're estimated probabilities. We can say that player A thinks the high price is more likely than player B. Okay, so that's the situation. What's the betting game? Well, it's to do with a possible contract between these players. So we're going to see some numbers, some W's coming along, and we might consider a contract between these players where money changes hands in a direction according to the sign of W. So if player B pays to player A an amount W, in other words, if W is 1, if it's a red dot, player B pays A something, but if it's a green dot, player A pays something to player B, as shown by this thing over here. This is the sort of direction of the arrows, show where the payments are taking place. then both players expect to make money, right? Because player A believes that red dots occur 60% of the time. Player B believes that green dots occur 60% of the time. And so both players in this situation expect to make money from this contract. It would be an attractive contract for them to enter into. Now, it is in fact equivalent to a contract for differences with a strike price of 0. And we'll come to more explanation of that in a minute. Now, this is titled Contracts and the Role of Risk Aversion. So I just want to make one very obvious remark here. That if neither player is risk averse, then both of them like this contract, and they both like it no matter what the Q, the quantity. So if we're going to do this for £1, we'll want to do it for £100 or £1,000,000. Now that's something kind of weird about that. You can imagine this kind of betting game. We don't know what the outcome of the next election is going to be, or we're kind of taking bets on what the timing of Brexit is, or something along those lines. And we have different views, right? And we believe that our views are correct. So we could imagine this kind of game setup being there in all sorts of environments.
I guess the outcome of a soccer game where a fan always thinks their team is going to win.
Well, it depends on the fan. You know, we can have pessimistic fans, but yeah. So what goes wrong here? Why do we not find enormous bets being made? Well, the answer is obvious, right? It's to do with risk aversion. So though I believe that I'm going to win 60% of the time, if I'm player A in this context, 40% of the time I'm going to lose. And so risk aversion is the thing which stops us from making really enormous bets. So I think that's quite obvious, but it's important in this context. So if we're going to think about contracts in a wholesale electricity market context, we can't ignore risk aversion. We can't sort of do this in a risk-free world. It really doesn't make sense in this particular context. So we have to have risk aversion. And that's the point I want to make from this example. But if you understand this example, you're understanding most of what I'm going to say. So what I'm going to talk about is very, very simple, and this example kind of captures the fundamentals of it. Okay, and please feel free to interrupt me and ask questions. Okay, so now let's think about how this works out in an electricity market. So if we look at electricity markets around the world, almost all of them have some sort of derivatives market supporting the wholesale electricity market. Now those derivatives markets become particularly important in energy-only environments, such as Texas or Australia, but in any case they're normally there. And if you look at the kind of derivatives being traded on those markets, the great majority, the most common derivative being traded, and increasingly so, is a contract for differences. So option type contracts of caps or collars or all these various different things are no longer really being traded in the way that people expected in many electricity markets around the world, but contracts for differences certainly are. So these are bilateral contracts with a strike price F, under which one party agrees to pay an amount of the difference between the actual price and the strike price to the other party. And typically these are arranged where W is the average, calculated in an agreed way over an agreed period. Now, a lot of derivative contracts have a payment up front and then a payment made after the eventuality occurs. Contracts for difference don't have that structure. The strike price is agreed up front, but no payments are made until after we find out what happens, in exactly the same way as that bidding or betting game that we described at the outset. Now, what is the right price? That's the right strike price. Well, clearly we want to kind of put this about where the expected price is. So if we have an expectation for a price for wholesale electricity in the future, that would be the strike price that we would choose. Now, most contracts, and again it depends upon where you are in the world, are over-the-counter style involving bilateral agreements, possibly arranged through a broker. Now, I said that we can't really think about a contract structure without thinking about risk aversion. And not only can we not think about it without understanding risk aversion, but we should also recognize that risk aversion plays the main role in the existence of these sorts of markets. So I want to describe that by saying that it's a hedging mechanism. So the idea is that these contracts will reduce the risk that an energy market participant is seeing from their normal operations. And it is often the case that a generator will have contract positions which cover the majority of its output. Again, this may depend a little bit from one jurisdiction to another. It certainly is the case in Australia. So, as I've tried to explain here on the second bullet point, these markets are in a sense driven by hedging behavior. Because retailers face a risk because they sell to their customers at a fixed price but buy at a variable price, they face a risk of when the wholesale price goes up, and generators are in the opposite sort of position. They face a risk when the price is low because they're not going to cover their costs. So because those incentives are opposite to each other, it means that in terms of the contract for difference market, we have what is sometimes called natural counterparties. These generators and retailers, or people that are heavy on the generation side versus people that are heavy on the retail side, are natural counterparties within this kind of wholesale contract market. And we'll talk about how that works out in a minute in more detail. Now, I have a sort of caveat here for people who have worked in this area. You may be aware of the fact that once you enter into a contract position, it changes the way that you behave in terms of the bids that you make into the wholesale market. That's a complication which I'm going to leave out. So I'm going to ignore the fact that the bids that you make in the wholesale market are affected by your contract position, and higher contract levels tend to depress spot prices. So I'm going to kind of ignore that and look rather at a more simple game because that'll make it easier to understand. So this is kind of by way of introduction, and so let me just kind of try and bring this together to say what I'm going to try and do in this talk and what the paper on which it's based aims to do. So we're going to try and investigate negotiations. How do we make an agreement? What do we agree on when we have different forecasts for the future? So that can be seen in an economics light as private information. We have private information about what the future looks like. And now that private information will typically come from a team of analysts who are working for us, or perhaps in today's world an expensive consultant who we're paying. It'll be based upon simulation sort of programs that will simulate the future, and it will take advantage. We're really interested here in the participants in the wholesale market, the people who are hedging their risks. So it will take advantage of the information that we have because we are a player in this market. So you can understand why it might be that the information here is not fully symmetric, and that it might be that we really do believe that we have other or better information regarding a future price than the person on the other side of the trade. And there's an interesting paper by Sander, Olsen, and Fletten, who do some analysis of the accounts of Norwegian hydropower companies and discuss the way that they make a lot of money out of this. Now, I don't know whether any of you know people who are traders in the electricity market world, or indeed in any world. The fact of the matter is that traders are kind of hardwired to take risks to try and earn money. So you might say to your trading desk, what I want to do is I want to hedge the risks here. I'm kind of worried about the price being high. I want to hedge the risk, so get me some contracts that are going to avoid me running a risk. Whatever you say, the trading team will be really concerned with making money. And so there is this kind of battle going on between the size of the hedge book and the size of the trading book in terms of what we're doing here. But this example at least demonstrates that it is possible to be making money out of these marketplaces, and we can't ignore that component in what's going on. So now that we've got a picture, which, just to remind you, the different components here, which kind of adds up into an intriguing whole. We've got information which varies on the two sides of the trade. We've got trades which have to be done because of the risk that is run if we don't make the trades, and trades whose characteristics are going to depend on our risk profile. And the question comes is, where do we end up? And how are we going to find out where we end up in that kind of context? And right at the end here, as I say, there's this kind of interesting question, is if I'm a generator who happens to believe that the price is going to be high in the future, perhaps I have some information about the likely availability of my own generation capacity, and I'm trading with someone else on the other side as a retailer. Does the kind of offers that I'm making indicate to the retailer that I have that kind of information? And does that impact upon the retailer's view about what the future state of the world might be? Okay, so that's the sort of aim of the paper. And we're going to be fairly simple-minded here. Again, we just think about a bilateral trade. I'm going to use A and B for the retailer and the generator respectively. And we have to think about two components of the outcomes for a retailer or generator. We have to think about the outcomes that emerge from the market itself, the wholesale market. If the price is high and I'm a generator, I'm making money in the wholesale market. So we have to take account of that. And we have to take account of what I'm doing in the contract market and whether I'm making money or losing money there. So we have to have these other things called RA and RB, which are I call them the operating profits for the two players in the state of the world W, which is going to be a future price scenario. We have a contract for difference trading at price F. We have an amount Q. So A receives, this is just exactly what we said before, A receives from player B this amount Q times W minus F. And okay, risk. How are we going to handle risk? Well, if you think about the structure that I started with by saying, look, what stops those contract quantities getting larger and larger, then you'll be aware of the fact that certain risk measures aren't going to do it for us here, because we can't have a risk measure, for example, if we're looking at CVAR, that would have the property that in the way that it's normally calculated, that it scales with Q, and that won't work in this context. So we actually need to go with a utility function, sort of old style utility function, to capture risk aversion. And I'm just going to use the utility function U. And these pi is normally a profit, but here it's an expected utility of the player A, which is a retailer. If that player signs a contract at strike price F for an amount Q, it will be the expectation of the utility which that player sees, which is the sum of money made in the normal operation plus the sum of money received, which of course might be negative in the from the contract. So I hope you can see that that is what I would be interested in maximizing if I was player A and down below player B with a change in sign of the amount received. Okay, so that's the model. It's really very simple. Yeah, so we're doing what mathematicians tend to do and abstracting away a lot of the structure here.
Why can you just use the risk-neutral measure and find the arbitrage-free prices?
Okay, so if you're going to find the arbitrage-free prices, you're going to end up with something very equivalent to this. So if you're taking a price view of the world, as would be typical for a financial analyst, yeah. So what you're doing there is you're choosing a set of probabilities really over the prices, which are adjusted in order to achieve that arbitrage. No, but hold on, I'm jumping ahead of the question, which is a mistake of mine. Let me rephrase this question a little bit, and hopefully I'm going to get what part of what Shmuel is talking about. Whenever we think about future prices, there is always this notion which says that the marketplace will arbitrage away any significant difference between the price in the market and the actual expected price. Here, though, we need to pay attention to the risk of the two players. Now, we might expect that F here will come out to be some sort of averaging of their prices, and you might be worried that if we have a marketplace for these contracts, that there would be other players, speculators, who would seize on an opportunity for any difference between the actual average and the price that these things are being traded at, and push those prices together.
Basically, in the previous example that you gave with the balls, the price will move to the point that both players, the one with the 0.4 and the 0.6, will see a zero expected value. So the price will adjust to reflect the difference in the distribution.
Yeah, these are it's not quite. Surprisingly, not quite. Let's come back to that at the end, because we could have quite a lengthy conversation, and I'd like to have that conversation, but maybe in the question time, about where these prices might end up. I feel it's good to kind of learn some new stuff here, and maybe some of you are not familiar with Nash bargaining. This is a picture of John Nash. There's a paper which appeared in April 1950, and you can see whether you think that this person looks a bit like Russell Crowe in the film A Beautiful Mind, and maybe the answer is yes, or maybe the answer is no. So this is Nash's first paper on this kind of games problem. It's quite short, it's 8 pages long. It's very easy to read and quite worthwhile to read. But for me at least, this is we kind of know about Nash equilibrium, but we may not know about Nash bargaining. So I thought I'd take the opportunity to tell you about Nash bargaining, because it's a thing that every well-educated person ought to know. And you won't be able to understand this by watching the film either. So, so Nash took this bargaining problem, which you can think of as how you might divide up a cake or something of that sort, and so how can we put this into an axiomatic kind of framework? So let's think about the nature of the problem. There are two players, and they're both presented with a set of joint actions. So they know what the options are, and if they select an option, they're both selecting that option. And for each option that they select, so that's the action, which I'm calling S here, an option in the feasibility set, they know, there's a complete information here, how much utility they're going to get. So in making this bargaining thing, I know how much utility I'm going to get from this action. I know how much the other player is going to get from the action. But one of those feasible actions is identified as what happens if we can't agree. Okay, so the government is negotiating with the Labour Party. What happens if they can't agree? So we're going to call that D, and we also know, perhaps the analogy won't stretch this far, we also know what the utility to the two players is if we can't agree. So we can think of the feasibility set as really just being captured by those utility numbers. So the U's and the V's here, which are just numbers, so they're real numbers and positive. Well, they don't need to be positive actually, but anyway, they're real numbers in the utility space. And because we can decide not to choose any of the actions, but to play a tossing coin type game between them, we can see that we should be able to have a outcome which lies between them. So that means that S is convex, and we're going to assume it's also compact. Sometimes it's convenient to rescale those utilities so that U and V are at the origin. And in terms of utilities, if you make an affine scaling, if you add a constant and multiply by something, then you don't change the, any of the decisions that you make. So let's think about a method for reaching agreement between the parties. And these are the Nash axioms. So this is what sort of properties should that method have. So he says the following: they all sound very reasonable. The method should produce the same answer for any equivalent utility representations. So if I just say, okay, all my utilities have got higher, but they're in the same relationship to each other, it shouldn't change the bargaining outcome. Pareto optimality, which is that we shouldn't be able to end up at a point where we could both identify another point which did better for both of us. Independence of irrelevant alternatives. If we end up at a particular outcome, we say, yes, this is the one we're going to agree on, and some other outcome that we didn't like gets taken out of the set of possibilities, that shouldn't change where we end up. That's really quite a reasonable assumption. And this one, which is very important in the proof, if the problem is symmetric, in the sense that for any option delivering an outcome U and V, then we could have another option which delivers the outcomes in the opposite way, then the method chooses a solution where both players have the same utility. So we can't end up with one player being better off than the other in those kind of circumstances if the problem is symmetric. If the problem is not symmetric, then that's fine, but if it's symmetric, those are the and the symmetry and independence of irrelevant alternatives go together because we can throw in extra options to make the problem symmetric, and that's how the result comes. And there's the result right down the bottom. Given those axioms, the method has to choose an outcome which is an X here, which maximizes a product, which is something called a Nash product, between the difference in the utility of player A between the outcome and what they would get in the event of no agreement, and the equivalent thing for player B. So we take that product. It's neat, isn't it? If you haven't come across Nash bargaining before, it's well worth knowing about. Now, this is another neat fact about Nash bargaining, which is that we can get to this solution using the following kind of procedure, which is alternating offers. I make an offer, you don't like it, you make a counter offer, I don't like that, I make a counter offer. Well, will this ever stop? Well, supposing we have a stopping imposed by someone else with a certain probability after every step. So if I don't like your offer and say no to it, there's a chance that we end up with this no agreement, D, in the previous slide, because someone comes in and says, stop, I've had enough, no more of these endless offers. Now, in the limit, where the probability of breakdown goes to 0, if we act optimally, which you could calculate using a dynamic programming kind of scheme, then we reach a Nash bargaining solution. Okay, so what would we reach as a Nash bargaining solution in the problem that we started from? Well, if we can't agree, then the size of the contract quantity is 0, and then it won't matter what F is. So, so here this thing here has got a 0 here, but actually it doesn't matter what F is. That's the non-agreement situation, and this is the Nash product, which is maximizing over Q and F. I want to compare that scheme, and I'll show you what the answers look like in a second, with an alternative, which is a simple broker mechanism. So here, this is the way it works. We submit our offer to a broker. The other person submits their offer to the broker, and the broker figures out what is going to keep us both happy. In the sense that we say our offer then becomes, at this price, this is the quantity that I would like. So there's now a simple kind of market mechanism that just clears the market. If I have already said what the quantity of contracts is that I want at a certain price for all possible prices, and the person I'm selling those contracts to has something similar, how much do they want to buy at all possible prices, then we just find the price at which those quantities match. Now, what should my offer be? Well, I want to maximize my utility. So for any given price, I can find the offer which maximizes my utility by taking the maximum, let's say I'm the retailer here, of the expected utility with respect to changes in Q for a given F. So this equation here is the first order condition that says what I would want to buy at a certain price, and we just find where those curves intersect. Now, in order to work out what actually happens, I have to be more specific about the utility function. Obviously, we can make lots of different choices there, and I'm going to choose a constant absolute risk aversion utility function where ux is equal to this thing. Rho A is what it was before, the retailer's probability of a high price, and in that case we can write down an equation for the curve that the retailer offers, the similar expression for the generator, and where those curves intersect is where we end up. So let's see what that looks like. Here's an example. I've set alpha equals 2 in the utility function. I've got a high price of 2 and a low price of 1, and I'm going to assume, just for round numbers, that the operating profit of the retailer is 1 at high prices and 4 at low prices. So the generator makes money at the high prices. Okay, so you can see this makes a lot of money. The retailer doesn't make much money, but if the prices are low, then we get the reverse, and RAWH is 4 and RAWL, the lower price. Anyway, it reverses. Okay, so if the differences of view about the chance of a high price is that A thinks that high and low prices are equally likely, but B thinks the high prices have a probability 0.6, this is what they offer, and this point here is where the broker will say, okay, this is the deal you've got, Q is 2, and this is the price. If we change the row B to be lower, then the generator's offer is reduced. So the offer of the generator goes down as their probability of a high price goes down. And we can see a kind of a sort of grid here of where these things cross over. And the red lines here are always generator lines, the blue lines are always retailer lines, and I've shown two extreme situations. If they both think that it's 0.6, then they end up with a Q value of 3 and an F value of 1.6, which is the common agreed expected price. if they both think it's 0.4, then they expect the price to be lower, and so it's not surprising that they end up with a lower price here. Okay, well, how do these differ? I've given you two methods. One is Nash bargaining, and one is submit to a broker. They differ, but only by a tiny amount. So in particular, under certain assumptions, the two solutions, that is the broker and the Nash bargaining, have exactly the same Q values, and the F values are really, really close, and they match exactly on the halfway line. So you can say we don't really care whether we have Nash bargaining and I ring up and make an offer and it's accepted or not and so on, or we submit to a broker. Those two would produce very similar answers. However, we need to come back to Nash. So this is where we're on more familiar territory, because even though if I'd asked for a show of hands, I would expect several people wouldn't know what Nash bargaining was, most of us will know what a Nash equilibrium is. Yes?
The result that you just mentioned,
Yep.
does that have nothing to, there's no assumption about the distributions?
Yeah, there are some assumptions about the way that those things are opposite. Have a look at the paper to see the detail. But yeah, I won't. Well, we can come back to that. Okay, so this was introduced in January 15th, 1950, with this announcement. This looks like the first page of the paper. It isn't. It's the whole paper. It's not really a paper. It's just an announcement in the Proceedings of the National Academy of Sciences, and an expanded treatment in September the following year. So a Nash equilibrium is a set of actions such that no player wants to change their action knowing the actions of the other. Well, here we run into an immediate problem, because the thing that we've just talked about, the broker mechanism, is not a Nash equilibrium. So we have a situation like this where we have probability of 0.5 for the retailer, 0.4 for the generator. This is the broker offer. But no, if I was the retailer and I knew that this was the offer of the generator, I would not choose this point. In fact, I would choose a point down here. And I don't have time to go through the detail here, so just please trust me on this. It isn't a Nash equilibrium. So actually I'd be better off kind of deflecting down a little bit like that. So it's not a Nash equilibrium, which is kind of awkward, right? We would prefer it was. So what would be a Nash equilibrium in these situations? Can we find out what that is? So I want to retain the idea that each player is submitting something to the broker, and the broker just decides where the crossover point is. So I retain that idea, but what I'm throwing away is that what they're submitting is the thing which is the Q value which maximizes their profits for a fixed F, which was where the broker solution originally came from. And instead I'm going to do it on the basis of a Nash equilibrium. So the idea here is it's kind of like more strategic in a sense. So we look at a best response, and suppose that we know the offer of the other person. So let's supposing that we're the retailer, we know the offer of the generator for a particular estimate row B, then that means a curve like this. So what's the retailer going to do? He's going to choose, so his blue curve, as it were, is going to be set by finding the best point on this curve. We can think about the highest value of this, which is the curve parameterized by t, what would achieve the maximum. Now, with a bit of work, we can find these solutions. So what have we done? We've thrown away the idea that we just submit the offer which maximizes our profit for a given price, and instead we've tried to take account of what the other person is doing, assuming full information. And we get an equilibrium in these offered supply functions. it'll be a complete solution which describes the joint behavior of the retailer and the generator. And best response means that with my estimate row A, the retailer's profit is maximized at the particular point where we cross over. Now, unfortunately, though we can find these solutions, they're not unique. So we've not got the niceness of a unique solution. So there's a whole continuum of supply function equilibria, and in fact that continuum can be parameterized with two parameters. So it's like a 2 degree of freedom continuum. What we might do, therefore, and especially if we had a sort of symmetric kind of problem, was look for the one which gives the best outcome. So what would be the best outcome for both players? In terms of the best outcome, we need to be slightly careful in how we do it, and I don't have time, unfortunately, to go through this slide. So just take away from this, we need to be careful how we calculate best outcome in the sort of way that's described on this slide. But hopefully you'll believe me when I say that we can calculate the best, the expected utility if players use a particular supply function equilibrium and recognize there are more than one. So I've now got a few slides which I'll go through quickly. Expected utility is 0.38 for this particular thing. This doesn't look very much like the diamond shape that we were showing before, which looked like it was straight lines, but which wasn't quite straight lines, but they were close to straight lines. So they're kind of quite pretty. I said there was a whole range of these equilibria, and this is how they look. They kind of, extend out according to where you go. Now, if you look at these numbers, 385, 601, that is the highest. So the highest that we can achieve, the highest expected utility is 0.385782. And it's useful to compare that one with what we had before, and that's that picture. So the scaling are not the same. But I've taken the one which achieves the highest utility, and the observations are twofold. First off, the best achievable expected utility is lower than the broker solution, and the volume of contracts is far less. So the Q values here don't get up above 3.5 instead of going up towards 5, and the range in prices is similarly reduced. Okay, now I'm watching the time, and I want to have time for some questions at the end. So I'm just going to very briefly introduce you the idea that I said at the beginning. Maybe we could learn from the other players' offer. And it makes a good deal of sense. If I'm offering a certain set of prices here, then I'm sort of giving away some information. So can we use that information? And I'm going to make a sort of supposition, which to make things easy to do the calculations. And the idea here that I'm going to play with is that though I have some private information, I don't believe it's of any higher quality than the other player's private information. So if I had their information as well, I would weight it equally with mine. So we're kind of putting ourselves on an equal footing. So that means that if I knew what row A was, that's my retailer estimate, my private retailer estimate, you're not going to tell me row B, but if you did, I would then revise my expectation to this row A plus row B. You don't actually have to tell me, because I can tell what it is from your offer. So it turns out that we can do a calculation of a supply function equilibrium in this case too. And it leads to, now if you're following the numbers here, these are even smaller numbers. So we're squeezing up here and we're squeezing up here. So the whole thing kind of squeezes down to be smaller contract quantities and a reduced range of contract prices. And we can play around with this one to try and get the highest value, 385, and now we go down again. So actually that one that I had earlier on was the best we can achieve. Okay, now this is for a particular setup. It's with a particular risk aversion. I put in alpha equals 0.2, and it has a particular set of operating profits, and we might ask ourselves whether that's consistent behavior. So we're getting very close to the end now, so just have a look at this penultimate slide here. So what we've done in this slide is to try different risk aversions, which between 0.25 and 0.3, or here's one with a higher value with a risk aversion 0.5, with different differences between how much money we're making or not in the case of the high prices. And here's the expected utility calculated in this complex way that I didn't describe to you, but I'm hoping you'll trust me on, if there's no contract. And this number here is the percentage improvement in expected utility if we just use the simple broker mechanism, which I can tell you in all these cases is exactly the same result as if we had Nash bargaining. And what you'll see is that all the way down here, the percentage improvement is bigger than it is if we have supply function equilibrium, and also bigger than if we use that sort of deductive logic. If the risk aversion is high enough and the difference in prices is high enough, then we may be able to push this other one across, and that becomes the highest. So what can we deduce from all of this? Let me see if I can bring this talk together with some conclusions. Well, first, it's an interesting model, up to me at least, but then it ought to be. We can spend some time on it. And it's the first time that as far as we can tell, that anyone has looked at derivative trading in this kind of context of private information, where traders are partly involved in hedging and partly trying to make profits. You know, which is kind of interesting in itself in a way, because if you ask how much a firm is making out of their electricity market operations, often this is the dominant determinant of whether they're making money or not. Very frequently, in cases where these markets are liquid, is hugely important for individual firms, and has been more or less ignored by the academic literature. And we've introduced this idea of direct bargaining, modeled by Nash bargaining, and observed that we get results that are very similar to a simple broker model. It's actually quite hard, to come back to the question there, to get very strong results that cover the ground of exactly when that's true and when it isn't true, but we are able to identify cases where it's true. And then we can find supply function equilibrium when we've tried to find a Nash equilibrium. But often, not always, but often, these produce worse overall outcomes in comparison with simpler non-strategic models. And when players combine their information, they're not likely to do any better. In fact, typically there's a reduction in contract quantities and the results don't improve. That's quite what we would expect. Why would you have a really large contract quantity? Well, you'd have it when you have a lot of difference between your views about the likely future. Differences in views here create a real incentive to trade large quantities. So you share information, you reduce the difference in views, you reduce the contract quantities, and unfortunately you were too small already, and this just makes it worse. Well, that's kind of an oversimplification. Okay, so it's a situation where everyone getting more clever doesn't actually help outcomes. Now, if I'm getting clever and you're not, then it'll be worthwhile to go through these kinds of analysis, but if we're both getting clever, then it doesn't necessarily help at all. It's 10:02 and I finished. Thank you very much.
Yeah, I think, a lot of the results are driven by your heroic assumptions here about there are only two players and all that. Because, like, for example, in pari-mutuel markets, or prediction markets, you go to the Iowa electronic market,
Yeah.
where there's a continuum of buyers and traders. the price is floating,
Yep.
and eventually the idea is that somebody, it's a binary outcome, so you can bet whether Trump or Hillary will be elected,
Yep.
and the probabilities are actually coming out of the price, because the price of the option, some people that want to bid on
Yep.
Trump are going to bid up the price until their expected value is zero, and some, so eventually you'll get with an equilibrium number of buyers and sellers, and the price reflects the probability, the consensus probability, if you wish, which is the equilibrium probability. And you don't need to assume risk aversion. You don't need to assume to know what the individual probability estimate is. The price determines the consensus probability.
Yeah.
How
So
can that-
the big difference here is that the players that are on either side of the contract are participants in the wholesale market. So if you imagine that you took out those R, capital R terms,
Right.
and I no longer care about whether there is a, what the outcome is. So you take out those terms, I'm a speculator, then you get very different results. So in this particular situation,
There's one speculator in the market.
yeah.
Would
Now, there's a very interesting question about speculators in these marketplaces. Now, I don't know whether there's anyone in the room here who has familiarity with this, and it's actually quite difficult to get information about some of this. But there's no doubt the volumes in these markets have typically dropped, and speculators have dropped out. And there's a reason for that, which is that if I'm the counterparty to a trade, and you, who I'm trading with, are a generator, you can influence the price. And I'm at a disadvantage as a speculator from being a counterparty in a trade in which you can influence the price, but I can't.
Speculators in your market. See, that's why we're doing virtual bidding in California, in the United States, because the virtual bidders effectively even the score by, you have enough speculators there which are risk neutral, and they are, so all the people,
Yeah.
the generators, they are going to, and eventually the speculators are going to determine.
Absolutely right. So if you can create a fluid market with speculators, then you can get rid of some of these problems and other problems too of market power. But the situation that I'm familiar with in Australia and probably in Texas at the moment is, I think, not quite reached that stage. And as I say, there are some dangers for speculators in these markets. Another question, maybe.
I'm
Yeah.
going to take the liberty. So you say everyone gets more clever, getting more clever doesn't help, but that's around kind of their anticipation. What about their prediction power? So if you give them more information and predictions become more accurate, how does that impact? If you have
Yeah, so no, that's it's the more accurate their predictions, the less they're more accurately they're going to be able to reduce their risk, and therefore they will certainly do better. So this is absent those changes. So getting clever in terms of better predictions is a good idea. Getting clever if your opponents are not getting clever in terms of trading decisions is a good idea. But it so happens that as the market as a whole, this is something that doesn't actually help overall utility.
And can you quantify the competitive advantage that comes from information in these markets at all?
Yeah, it's the problem is you can, but you're just dealing with cases. I can give you a case and I could quantify exactly everything about it. But it's there probably is some monotonicity results, but we haven't pursued that. Yeah.
So by looking at the outcome, or more specifically the prices and the volume, is it possible to deduce the private information of the other counterparty in this setting? Which is the usual way Radner wrote in his rational expectation equilibrium, that if you have parties bidding in the market and then the prices can reveal the information of all the players at the end of the...
Yeah, so if I'm understanding you correctly, we've got a more complicated situation than those standard ones about prices giving valuations, because we've got prices and quantities. So it does turn out that it works still. What we do is we say an equilibrium is between a set of offers and another set of offers. So if we imagine you saying, what your bids are, your complete offer curves for different probabilities, okay, then I know you're playing a complete set of offers. Okay, now I make an offer against you, and then I can see what the market would end up at for a particular value of your probability, because it would be a particular curve. And I can say, am I at the right spot, given this rho A plus rho B over 2 kind of calculation, and move it accordingly. So if it's an equilibrium, it has to be, no move is going to be better. So it's an equilibrium between two sets of offers. And we get these lovely pictures. Yes, Claudia.
I wonder what is behind this, everyone getting more clever does not help. Is the fact that they are all getting clever, or if they all get dumb, it also doesn't help. You see? It's the fact that they are acting the same.
Yes.
All of them.
Yes.
It doesn't matter if it is clever or dumb.
That's an interesting question. It's certainly to do with the fact that they're acting the same. Yes, I think that's part of it. It's a little bit hard to get your head around here, because what's happening is that the best mutual choice of contract. I mean, there is a best mutual choice of contract, and it's larger quantities than they seem to want to get to when they are in this world of optimal responding. So the optimal responding is they're kind of shading their quantity offers because that looks reasonable given what they're facing, and they end up not making sufficient quantities, and I don't know quite what the equivalent would be to be dumb, right? I'm not sure how you would model that. Easier to model being clever than it is being dumb.
You don't have to model it.
So we could take some randomness. We could throw randomness at it. I guess that's what we would do. We haven't done that.
Okay, I think that's the last one.
Okay, thank you.